We will cover robot programming applications workflow. We will walk through a end-to-end. We will start with a customer showcase, which will then be followed by a demonstration, a live demonstration. The demo will cover setup and preparation of a part for CAM programming, and then we will walk through programming 3 to 5 axis toolpaths and post-processing apt code. And once we're done with that, we will actually switch over to IRBCAM, where we will show how to define a robot station using IRBCAM's wizard interface. And we will also transfer the CAD model data and posted code from Microsoft CAM to IRBCAM. And once we've done that as part of the workflow, we will then do programming, robot programming. We'll show that in IRBCAM, where we will be configuring targets, verifying motions, outputting code from IRBCAM to the controller. And we're also very excited to tell you that we're going to have a robot in motion, and you will see that today as well. In terms of the applications workflow, we will start with a part that is designed in a CAD system, such as Rhinoceros, Visual CAD, or SolidWorks. Today, you will see Rhinoceros being used. However, you can use your own CAD system and bring the CAD model data into any of Microsoft's CAM products so that you can generate the toolpaths. And so it's important to keep in mind that you have that flexibility, although today's demo, we will be showing you Rhinoceros and RhinoCam. Then once the CAD model data is prepared, you will see our Uday showing how to generate 3 to 5 axis toolpaths. And once the toolpaths are generated and verified, they can be posted as apt code and brought into IRBCAM along with the CAD model data. And Uday will walk through all of these steps in a live demo. And using the toolpath that's brought in from Microsoft CAM into IRBCAM, we will show you how you can easily program a robot using the IRBCAM wizard interface. And as I mentioned earlier, last but not least, you will actually see a robot in motion today as the final part of our presentation. Okay, as I mentioned earlier, we are very excited to have 2 special guests with us today. We have Gordon Barnard, designer and engineer with Savsu Technologies, which is located in Albuquerque, New Mexico. Gordon has been successfully using Microsoft and IRBCAM products in his design and engineering work, and he will talk to us about how he is using these 2 products in production. Next, we have Geir Hovland, who is a robotics engineer and developer of IRBCAM with Mechatronics Engineering Limited, and he is joining us today all the way from Norway. And Geir will be able to address questions regarding IRBCAM, and he will also be demonstrating the robot in motion today. All right, so from the Microsoft team, we have, in addition to Uday, who will go through the demo, we also have Joe, who's available to help answers that are posted during the session. All right, so at this point, we are ready to get started. And Gordon, we will have the presentation handed over to you.
Hey, Krish, thanks. Hope everyone can hear me. I guess I just wanted to start by saying thanks to everyone at Microsoft who puts these things together. I know it takes a lot of time and energy, but speaking personally, I know that on more than one occasion they've been helpful to me, so I think I speak for everyone in saying thanks for doing that. So my name's Gordon Barnard. My company is Savsu Technologies, and we're a design company that specializes in medical technology, and specifically we have a focus on cold chain solutions. So essentially we create shippers for payloads that have to be kept at a very specific temperature or within a very specific temperature range. And that can mean anything from vaccines to biologicals, living cells, blood, that sort of thing. So it's big, it's big and important stuff, and the implications are high. Our shippers are typically, we use super insulators. We do a lot of plastic thermoforming. One unique thing that we also do is we incorporate electronics into our shippers, which allows the user to have constant access to the shipper's location anywhere in the world. So we do GPS tracking. We can do temperature monitoring, internal temperature monitoring in real time. We can establish geofences. We can check for shock, tilt, all those things. So really the idea is that these really important payloads, which can mean years of research or even somebody's life, we're doing as much as possible to give the user a lot of control. So my specific position within this company is one of a designer, engineer, fabricator, technician. I sort of have a unique role in that I'm able to track a design from conception all the way to manufacturing. And it's our process that really allows us to do this, and the fact that we're still a relatively small company, but we work light, we work fast, and I'll get into that in a little bit. But I'll talk about my background. I started out with art and design training and building construction, and I guess the two of those in tandem led me to architecture. And it was really during my architecture education that I started to understand building systems, learned how to operate with CAD. I started to learn about CNC and rapid prototyping, 3D modeling, all of that stuff. So that education really prepared me well to be in the position that I'm in now, although I don't by any means consider myself an expert yet, but we're getting there. So the way that we work at SAVSU, we do a lot of rapid prototyping, and I think you just saw an image of our robotic cell. We're using an ABB 4400 robot, and I just wanted to sort of walk you through what our process looks like. Typically, it starts out with a product idea. That can come internally or externally. Either we have an idea for a product that could create a market shift, or a customer comes to us with a specific need and we can create a custom solution for them. So we have the product idea. We will then have a design meeting where we all sort of congregate around a table, computers, sketchbooks, whiteboard, whatever, and we kick the ball around and really talk about how we can best create this product to suit the needs. But essentially, we have a design meeting, then I'll take that into a design period, which is where I start to get into the CAD and the modeling. I use Rhino. I have for a long time. It's what I'm comfortable with, and I think it's a really capable program. But essentially, I'll end up modeling a geometry. We'll do a pre-review so we can really study the geometry. It starts to become tangible at that point, and we can check tolerances and look at volumes. We can crunch numbers related to thermodynamics just to ensure that what we're doing kind of supports the initial aim. But assuming all that goes well, I can roll that into the CAM and rapid phase, which is where I start to set up tool paths. So I'll bring my 3DM, my Rhino geometry, into Rhino CAM, and I think you see a screenshot of that at the moment. You can see me setting up some tool paths for a part, and that's exactly what I'll do. I'll walk through all the steps, how this thing needs to be created on our specific machine. And one thing I've realized is that it's kind of different for everyone depending on your setup. You know, you may need to sequence things differently. But once I have all my toolpaths set up, I'll export those files as APTs from RhinoCam, and I'll import them into IRBCAM. IRBCAM is where I can set some of the robotic controls and check for collisions, all of that sort of thing, with the aim being that it will convert that APT file into a rapid code file. The rapid code file is what the ABB robotic system understands and operates on. So there will be an exported file from IRBCAM once I've configured my path and walked through all of those steps. After a little bit of doctoring, I FTP that over to the robot, and I will have set up my stock material, which matches what I have in RhinoCam. And I will mill a part. Typically, we use a lot of thermoformed plastics for our products, and we have a thermoforming machine literally right next to the robot. So a lot of times what I'm milling on the robot are molds. So in the previous slide you saw the product that I was working on. That geometry is actually a mold. So the top right-hand image is the part that I milled on the robot, and below that is a plastic part using the mold above. So, you know, now we have a real tangible part to look at, and I will either hand trim it or I'll have a robotic operation to do a robotic trimming, which can be really nice for plastic parts. Or sometimes, you know, it's a variety of parts that need to be milled, molded, assembled in order to create the one product that was the idea in the first place. But anyways, after this step, we go back into a design review, and you know, the cycle continues. So that's kind of just a step-by-step of how we work at Savsu. And believe it or not, that whole sequence can sometimes unfold within a day. You know, sometimes we're working quickly and we can really just get after it. And that speed is what allows us to, I think, be competitive in this field, especially considering our size as a company. As I said before, we're lean and we work quickly, and that gets us pretty far. The other thing that our company does or can do, we have the capability of providing custom solutions for customers. So a lot of our customers are scientific entities, researchers, pharma companies. They can send us whatever it is that contains their payload. It can be a vial or a vial rack or a cassette or a blood bag or a syringe. It doesn't matter, whatever it is, and everybody uses something different, you know, but they can send it to us or they can send us specifications, and because we do this type of work, we can model their payload, we can thermoform a plastic part, which could be the liner. So you could imagine it like we have a shipper, we have a box, super insulated box, and the internal volume in this box is the exact same shape as the customer's payload, which is good for a variety of reasons. So our products, I don't know, I think they really promote a lot of freedom and security, a lot of visibility, interchangeability, ultimately a lot of control for the user, for the customer, and the software has really allowed us to work this way. You know, I think a conjunction of RhinoCam and IRBCAM has allowed us to work quickly in an area, robotics, which I think most people consider robotics as something that is meant to do one task repeatedly over and over because the setup can be so tedious. But for instance, in RhinoCam, I have a variety of templates for doing different jobs, just depending on the size of the part or the types of motions that the robot is doing. We've really found ways to cut time out of the equation and use robotics to our advantage, which ultimately gives us a lot of flexibility. So that is pretty much it. I guess at this point I will hand it back to the other panelists. Thank you all for listening.
Thank you so much, Gordon. We really appreciate you joining us today and sharing your experience with us. Before I turn it over to Uday, I just wanted to remind the participants that you can go ahead and type in your questions through the chat window. And as I said earlier, we will try to answer them during the session. If not, we will definitely get back to you after the session. All right, Uday, all yours.
Thank you, Krish, and thank you for the nice introduction, Gordon, as well. So, folks, as you can see, Mexoft's CAM product and IRBCAM can be used for a wide range of applications for programming robots and robotic arms for different application. And you did see here one of our customer success stories in here as well. So today we will be going over the entire workflow of how to use Mexoft CAM products for taking your CAD design model to generate toolpaths using Mexoft's CAM application and then transferring that data seamlessly into IRBCAM to program the robot and taking that information to your robot controller. So without any further delay in here, I would like to demonstrate RhinoCam in here today. RhinoCam is a flagship CAM plugin product that works completely inside Rhinoceros. Rhinoceros is a solid surface NURBS modeling CAD system, and RhinoCam plugs directly into Rhino as a fully integrated plugin. Now, you could be using our standalone visual CAD CAM application where you can bring in CAD data from different CAD systems. You could be using UG, CATIA, any of the CAD system and bring it in your CAD files in a global exchange format. It could be IJust, STEP, STL, Parasolids. So you could import them and program toolpaths. Or if you happen to be using SolidWorks, you could use our gold certified CAM product, which is visual CAM for SolidWorks within SolidWorks interface to program your toolpaths. The workflow in these CAM systems developed by Mexoft would be very similar, but today for this webinar I'll be covering RhinoCam. So as you can see here, I have a scanned 3D model in here imported into Rhino. And as RhinoCam starts up, you'll notice the RhinoCam menu appears at the top of your screen, and also the RhinoCam's machining interface shows up over here on the left half of the panel in here. Now, RhinoCam offers milling, turning, nesting, and art solution for programming for robots. Typically, you would be working with our mill module. Our mill module offers 2 to 5 axis programming solutions. So we have different configurations. So if your application only requires 3 axis, you can choose the configuration that's suitable for 3 axis. We have 3, 4, and 5 axis application modules available for your application needs. So the workflow in RhinoCam is using the machining browser in here. We have 2 main tabs, Program and Simulate, and we work our way left to right as we work through these commands in the ribbon interface in here. The typical step here is first to define your machine tool. We could define 3, 4, or 5 axis depending on your type of application. So if you're going to be using a multi-axis robotic arm and you like to program 4 or 5 axis toolpaths, you can choose the number of axes accordingly. The next step is to establish your post-processor. This would be the output format to be able to output your program toolpaths to IRBCAM. You would want to set the post-processor to apt-cls, and you would set the file extension to apt. This would, once your toolpaths have been programmed, you would be generating the output file in .apt format from RhinoCam. In the next step, we would like to build our workpiece, which would be the stock material. So you would go over to stock, and for this application, I'm going to use a cylinder stock right in here. Enter in the parameters, which would be the stock radius and the stock length. You can establish these parameters. And then when you select OK, the stock is defined, and as you can see, the stock overlays on top of the part geometry. And each of the information that you programmed is automatically updated under machining job. In the next step, we are now ready to program toolpaths. Now I would like to go over different techniques for programming this part. Typically, I would want to rough it from different orientations, so we can use 3-axis operations to rough this part from the top, from additional orientations from the front, back, and from multiple different orientations. So we'll start with the roughing process. So I'm going to go over to 3-axis, and you can see that RhinoCam offers a wide range of methods in 3-axis for roughing and finishing operations. So I'm going to start out with the roughing operation in here, select horizontal roughing. And in this particular process, I could specify the tool, set the feeds and speeds, establish the clearance, specify your cutting parameters where you can set your tolerances, stock allowance, your cut patterns, your step overs. In the cut levels, you can also choose how far down you want it to cut, and you can also graphically pick a point here. So I would like to restrict it down to just slightly below the eyes over here on this model, and I can specify the additional parameters for engage and retracts, and then selecting generate will compute the toolpath. So in the process of roughing, the system automatically takes into account the stock that you define and analyzes the part geometry and figures out your roughing toolpaths. So there's a roughing toolpaths. It's roughing it out in layers or levels. This is also known as roughing in levels, or also known as Z-level roughing operation in here. So once you have the operation programmed, you could switch over to the Simulate tab and run a verification in here by selecting Play, and this shows your cut material simulation or verification in RhinoCam. So as you can see, the roughing operation is being programmed in steps. At any point of time, you could select Pause and then go to End by selecting Simulate to End. So we now roughed it out using a 3-axis roughing operation from the top. Now we would like to go ahead and program this from additional sides or additional orientations in here. So I would switch back to the Program tab, and I'm going to go over to the Setup and orient my coordinate system. So you can see now the Z-axis is currently normal to the XY plane. I'm going to go over and orient the setup and rotate it 90 degrees on X. So now you can see that the Z-axis is normal to the front face. I could now create additional roughing operations. So in this particular process, I'm going to start with a re-roughing operation in here, where the system automatically takes into account the stock that's being left from the previous operation, which means it takes into account the in-process stock, the material that's being left from the previous operation. Similar workflow, you establish your tool, feeds and speeds, your clearance, establish your cutting parameters, and then selecting Generate is going to create your roughing operation from the additional orientations we chose to program it from. So now we are roughing it down from the front face. We'll switch over to the Simulate tab, select Play, run verification. Now this type of machining from different orientations is also known as 3+2 machining, or also called index machining. It's commonly called index 5-axis or even 3+2 machining. So we have the roughing programmed from one additional side, so I'm going to simulate to end, and I'm going to go back and repeat the same process to rough it out from an additional orientation in here as well. So go over to Setup, add a new setup, and change the orientation in here. I'm going to flip it over by 180 degrees so I could rough it from the back of the part. I set that right there, so we have a new orientation. I'm going to repeat the same operation, re-roughing, specify the tools, establish the feeds and speeds, the cutting conditions, and then select Generate to program the toolpaths. So we now have a roughing operation being programmed from the back half of the part as well. So selecting Simulate and Play gives you the cut material simulation and verification. So I'm going to select Pause and Simulate to End to run through the simulation. Now once you have these roughing operations programmed, and if you're ready to go ahead and transfer this over to IRBCAM to program your robot, what you would typically do is post-process these operations from RhinoCam. So you could select the machining operation, right-click and select Post All, and you can specify a file name. Automatically it grabs the name of the part, and I'm going to hit Post, and there's our posted output file in here. So it's output in AT format. I would also export the part model as an STL file, and it can be then translated into IRBCAM seamlessly using the CAD converter application that comes with IRBCAM. Now I'm going to go ahead and start up IRBCAM by selecting the desktop shortcut that's found on my taskbar, and IRBCAM starts up and displays a wizard interface at the start. So you can either open an existing saved station, or we could define a new station by using the wizard. So we'll select the new station wizard and select OK. Now in the next step, you could specify if the station has a linear track or it does not. So in this particular step, I'm going to choose station without a linear track and choose next. Now this is going to go ahead and load the IRBCAM interface and allow you to select robot from the library of robots. IRBCAM currently has over 200 robots that are in the list here. As you can see, they're most all the popular names. You can find it: FANUC robots, you have ABBs, you have KUKA robots, Motorman, Stably, a wide range of robots. And you can, if the robot that you're looking for is not found on the list, you're welcome to send us an email, and we can check if the specific robot model and the controller can be supported and added to the library of robots in IRBCAM. So for this particular demonstration in here, I'm going to go over and select the 2600 ABB series in here as the robot. So once the robot is selected, you'll see that the robot model is previewed on your graphics screen right in here. You can use these controls to pan and zoom and rotate. If you also have a space pilot or a space navigator, a 3D mouse, you can use that as well. And you can specify the initial position, the robot position. By default, it's at the origin, which is 000. And then you go ahead and select continue over on the lower right corner of your screen. So once you define your robot, the next step is you specify whether the robot holds the tool or if you have a stationary tool. In this particular step, I'm going to choose the robot holds the tool and select next. Now this would allow you to select a tool from the library of tools that are already included with IRBCAM, or if you have a custom tool, you could model it in CAD and then you can convert it and also import it using the import option under the file menu right in here. Now for this particular robot, I'm going to choose the standard spindle in here, and I have the tool selected, and we'll select next or continue. And here you can specify if you have a rotary axis or not, and we'll go ahead and select the rotary axis, the station with the rotary axis for this particular example, and we'll select next. So now it allows you to specify a type of rotary axis in here, and I'm going to use a vertical axis for the rotary axis. So it's like a turntable, and specify the position of the rotary axis in here. So I'll specify the XYZ coordinates of the rotary axis and then select next. Now I can also load the part geometry in here, which is as defined as a user object in IRBCAM. I'm going to choose station with a user object, choose next, and I'm going to go ahead and load the model, import the file that we exported from RhinoCam. So you could go ahead and select the model. You can use the CAD converter from IRBCAM to convert it from an STL format to IRBCAM's native format. So you just have to load the file and then save it out as a CAD model. So you can see that the part is now loaded. So the part that you modeled and programmed in RhinoCam is now transferred into IRBCAM. So in the next step, we'll go ahead and specify if you'd like to add any cubes, tables, or fences. I'm going to select no more cubes and select next. So I can now go ahead and save this out. In here, I'm going to select save, and this is going to go ahead and save the station information, the robot station, and the geometry in IRBCAM. So when you're ready to program this part, you could actually load it from a station rather than having to go from a wizard in here. So we have the station defined and the part geometry is automatically inserted in here. So let's go ahead and load the G-code or the apt file that you posted from RhinoCam into IRBCAM. So you could go to the file menu, select apt, and you can use load apt. IRBCAM can also take in a G-code and also translate it into apt as well. So in this particular demo, I'm going to use the load apt format, and I'll go ahead and bring in the apt file we just post-processed from RhinoCam. So when you import or load the apt file, you'll be prompted with this dialog which would allow you to specify the minimum distance between your robot points. You can set this, you can select it from the list in here, and then select OK to accept it. So this automatically transfers the information which would then allow you to establish and configure your station. So you can see that all of the points in here that you imported are converted and then loaded into IRBCAM. In the next step, you can specify your tool geometry. Your tool data can be set right in here. I'm using an end mill. I'm going to specify these parameters. If you need to change your tool position in here, you can do that. And there's your tool defined. It's a 1-inch end mill. I'm going to go ahead and then configure the path. So selecting tool and configure path will allow you to establish your initial orientation, initial configuration, and based off that you can choose these options where you can set your tool roll angle. If you wanted to do a wrist up or wrist down, you can choose these parameters, and also you can set the rotary axis mode in here as well. So with these parameters set, I'm going to pick OK, and you'll notice that it's configuring the path, and once it is successfully able to configure all the paths, you will see a confirmation message saying all targets have been configured. And once the targets are configured, you'll see that these joints automatically are all turned into green. You could now go ahead and run a verification by selecting animate, and this basically gives you an animation of the motion. And you can see that this automatically runs through these points, joints, as you see over here on the left pane. At any point of time, you can also pause it. You can go over to targets, and if you want to skip, you can say go to target. You can use these controls in here to skip forward, accept it, and then select animate to continue your animation. You can see now it's programming the roughing operation towards the back of the part. Now once you have all of these programmed, you're now ready to transfer this out to your robot controller. So you would go over to the file menu, go down to ABB, and select Save Rapid. Now ABB robots use Rapid as their control output format. Other robots could be using different formats. So IRBCAM supports over 200 different type of robots. So the output formats for each of those robot controllers would be available in those suitable formats, depending on the robot station that you define. So here the rapid code is generated, and once the code is generated, you can preview the code using a text editor. It could be Notepad or Notepad++ or any text editor of your choice, and there's your posted output file from IRBCAM as you see it, and this information can then be transferred over to the actual robot controller. So here what we looked at was programming 3-axis toolpaths from different orientations, also known as indexed machining or 3+2 machining. Now to program a finishing operation on this model, we could, since we are using a turntable on the robot, we could use a 4-axis operation, like a 4-axis finishing operation, to program it. And let's go over and take a look at how we could program a 4-axis toolpath in here. So I'm going to go back and switch over to RhinoCam. And here I have a 4-axis operation pre-programmed. It's called 4-axis parallel finishing, and you can find these under the 4-axis methods. There are a variety of different 4-axis methods you could program. We have drive surface machining, 4-axis engraving, parallel finishing, R-level finishing, and also facing pocketing profiling. Now for this particular model, I've programmed a 4-axis parallel finishing toolpath, and let's go ahead and run a verification of it in here. So I'm going to select it and then go to play, and you'll see that the tool remains normal to the rotational axis. So as you're programming it, the table, you can have the rotary table turn back and rotate back and forth to be able to reach out to all the areas on the model here. So this is a 4-axis parallel finishing toolpath, and you can see the simulation of the 4-axis toolpath in action in RhinoCam. And if you'd like to speed up the simulation, you can use these controls in here to speed it up, to have it go faster or slower in RhinoCam. So once you have these 4-axis toolpaths programmed in RhinoCam, you would go ahead and post-process these out to apt.cls from RhinoCam, and then we will transfer the apt output from RhinoCam to IRBCAM and configure the configure the station and configure the targets. So at this point, I'm going to hit pause to pause the simulation, and I'll post-process this output into IRBCAM. So I'm going to post it, and there's the posted output file, and I'll switch back into IRBCAM's interface, and I'll go up to the file menu. Now, since I already have the defined the station and the part geometry is all defined, all I got to do is go back to apt and choose load apt. And I'll go ahead and select the finishing operation we just posted, select open, and specify the minimum distance between the robot points. Click OK to accept it. Now, if you wanted to append the finishing operation to the roughing operation, you could have chosen append in the options dialog that just popped up. So we have all of the points, the motions loaded in here. In this step, we want to go ahead and configure our targets. So we'll go over to Tools, and then we'll select Configure Path. Now, right in here, I could specify the different options for configuration. So for the initial orientation, I'm going to set my tool roll angle to 90 degrees. And I'm going to set the wrist to be wrist down. As you can see, it changes the wrist position. And rather than using a fixed angle, I'm going to pick a dynamic angle which would allow the turntable to be, the rotary axis to be rotated in here. And I'm going to go ahead and accept that. So now the path is being configured in IRBCAM. Once the path is configured, we can now run a verification. So all the targets have been configured, and let's run an animation in here. So you'll now notice that the part is being rotated on the rotary axis. So you could use 4-axis toolpath methods with the turntable to program your robot for machining for applications like these which require machining from multiple different orientations. At any point of time, you can hit pause. You can also skip through some of these target positions in here, and then click OK to continue and animate it. You could also use these controls to zoom in and zoom out as you're performing the animation. The next thing I would like to demonstrate is how we could use RhinoCam and IRBCAM for programming a simultaneous 5-axis application as well. So I'm going to go ahead and pause the simulation right in here, and we'll switch back to RhinoCam. And I'm going to go ahead and bring in another model. I have a prototype model of a car right in here, as you can see. And I would like to program the surfaces on the top of this model in here. So we have a wide range of 5-axis toolpath methods, starting with curve projection, flow curve, between curve, surface normal, swerve machining. So I have a between curve machining operation toolpath programmed in here for the top surfaces. And let's go ahead and run a verification of this in RhinoCam. So I'm going to hit play to run a simulation. So you'll notice that the tool remains normal to the surface being machined. So this is a true 5-axis, or also known as a simultaneous 5-axis machining operation. So RhinoCam can be used for programming 2 to 5-axis operations, machining operations. In this particular case, we are programming a simultaneous 5-axis operation in here. We could also be using a swarf machining operation to program certain areas using the side of the cutter. So this is what you're watching in the simulation is a between two curve machining, which is a true 5-axis method. Now here's an example of a swarf machining operation in program. So let's go over to IRBCAM. Let's post-process this toolpath from RhinoCam in apt format. And I'm going to go ahead and save this file in apt format. And you can see your true 5-axis motions has these go-to motions with the coordinates and the IJK values. We'll now switch over to IRBCAM. And I'm going to go over to the file menu. And I'm going to select open station. So I have a saved station in here. And I'm going to choose the station as car model and load it. So you could either start by creating a new station wizard, or if you already have an existing station defined, you can go ahead and load the station in here. So the station is loaded. I already have the part model. I also have a cube that's defined in here, and the toolpaths, the target point, the toolpaths have already been loaded in from RhinoCam into IRBCAM in apt format. So I'm now going to go ahead and establish my tool data in here. This would be a ball mill 1/2 inch. I'm going to accept that, and then we'll configure the path. You can select configure path and select OK, and this would configure the path and ensure that all targets are configured. So if some of the targets cannot be configured, it'll automatically identify those targets. And you can also use the optimizer in IRBCAM to help you configure the targets. So here we have all of these targets configured. And now let's go ahead and run a verification. So I'm going to do an animation right in here. You can see the simultaneous 5-axis toolpath that you program in RhinoCam is transferred over to IRBCAM, and you can see a multi-axis motion as it's programming is machining the top surface of this car model. Folks, if you do have any questions during this webinar, please feel free to post those questions in the questions panel, and one of our panelists will be more than happy to answer them for you. So you can take a look at the simulation that's being in progress. Now the next thing I would like to go over here is what if you had some fences or additional cubes, and how IRBCAM can efficiently detect collisions for you in here. So I'm going to pause the simulation for a moment, and I'm going to go ahead and add a cube. I'm going to select add cube from the edit menu, and I can specify a color for the cube. I'll just go with the default color. And now I'm going to define my cube by specifying the dimensions for the cube and also the position for the cube. So I'm going to go in to set the XYZ coordinate position of the cube. So I'm going to enter in the properties for the cube right in here. So you can see that I've defined a cube like a wall right towards the front of the part right in here. As you can see it, I'm going to pick OK to accept it. So I have a cube defined right towards the front face of the model. So now if I'd like to go ahead and check for collision in here, I can go into Tools and select Collision Detection right in here, and I can specify from and to targets. I wanted to check for a few areas for collision. I'm going to pick OK to accept it, and in this particular step, IRBCAM is going to analyze and check for collisions between the tool and the cube. And if there are collisions found, you'll see that the collisions are determined, and it automatically displays in a text editor. So this gives you a quick overview, a demonstration of how RhinoCam and IRBCAM can be used in conjunction for programming robots. I would now like to invite Geir Hovland from IRBCAM to give us a robot in action live, so our attendees can view the actual machining of this part.
Yes, thank you, Uday. Can you see my webcam?
Yes, so I can. Just for our attendees, you should be seeing a webcam in the same window application that you're watching the demo. You're welcome to resize it so you can, so that resize it to fit your screen resolution to view the live webcam in action.
Yes. So as Krish said in the introduction, my name is Geir Hovland. I'm based in Norway. And the time difference is 9 hours to California. So right now it's 5:45 p.m. over here. The webcam you see is from our development lab. We have a ABB IRB 1400, as you see in the picture. And it has a small lightweight spindle, which is only 3 kilograms, because this robot here has a maximum payload capacity of 5 kilograms. And also this spindle is air-cooled. It has a fan at the back, so there's no extra pressured air cooling on this one. In addition, in our lab we have additional robots. We have a KUKA KR125. We have robots with turntables. And on the right-hand side on my webcam you see the edge of a track motion as well. And all of these robots, we just use them for development of the IRBCAM software. At the back of the webcam, you see a part which we made with a turntable. You see at the back there. It's an example. So I think now I will just start the milling. Compared to Uday's configuration, what I did, I rotated the tool roll angle by 90 degrees. Because otherwise I would get a collision between the spindle and the upper arm. But by rotating it like this, as you will see when it moves, there will be a collision-free path. Okay, so let's start it. So now the spindle starts. And normally I would do the roughing first, but because of the limited time we have in this webinar, I'm going straight for the finishing. And we have a special tool here which allows us to do 2-inch depth. And the material here is styrofoam, and the depth of this plate is about 2 inches thick. So now it's doing the 5-axis continuous path as programmed by Uday. He just emailed me the rapid code, and I just used FTP, file transfer protocol, directly onto the control system. In addition, IRBCAM supports spindle speed. So the RPM information is stored in the apt file from RhinoCam. It's automatically programmed into the spindle to get the correct RPM. Also, we support automatic tool change. But this spindle we use in this webinar does not have automatic tool change. But in another setup we have a tool change cabinet with up to 20 different tools, and they can all be selected automatically via IRBCAM. Okay, I think I will just mute my microphone now and hand it back to Uday. Is that okay?
Thank you, Geir. That would be fine.
Thank you so much, Geir. Really appreciate you joining us and going through the demonstration of the robot in action. Again, this is Krish, and I just wanted to remind everybody that you can type in your questions in the questions panel, and we would be happy to answer any questions that you might have.